The 8 Laws of the Universe. Hello everyone and welcome to my channel. From the tiniest quantum ripples to the most massive clusters of galaxies, from the operation of atoms to the rotation of galaxies, every detail is so perfect. This ubiquitous precision and harmony make up the magnificent music of this vast universe. What is even more amazing, however, is that these seemingly cold laws of the universe weave a miracle. Someone once said, "There is no chance in the universe. Everything is a product of rigorous laws." This statement profoundly reveals the mystery and order of the universe. The birth of every galaxy and the burning of every star silently follow these invisible laws. Today, we will explore the 8 laws of the universe together. 1. Speed of light limit. The speed of light sounds like a theorem or an invariable law in our daily lives, as remote as the stars in the sky, right? However, if you delve into the principles behind the speed of light limit, you will find that it is not just a formula or an assumption by scientists, but it is inextricably linked to the structure of the universe, the nature of matter, and the relationship between time and space. What is the speed of light? The answer is simple: about 299,792,458 meters per second. To use a more graphic analogy, if you were to travel from Earth to the Moon at the speed of light, it would take you almost 1.3 seconds. Sounds fast, right? But let's imagine that at that speed, even to get to our nearest galaxy, Proxima Centauri, it would take about 4.22 years. Yes, more than 4 years. So, while the speed of light is very fast, that's still a long time to travel through the entire universe. This begs the question, why does the speed of light have such a strong limit? Why can't we explore the universe at a faster speed? This question begins with the scientific revolution of the early 20th century. Our good friend Albert Einstein, a physicist with a big head, put forward the concept of theory of relativity, which revolutionized our understanding of the universe. Especially in his special theory of relativity, he clearly pointed out that the speed of light is the speed limit in the universe. Simply put, no matter in the universe can exceed the speed of light. This is not just his personal opinion, it has been verified by numerous experiments and has become one of the cornerstones of modern physics. Let's take the simplest example to illustrate. Imagine if you are riding on a train that is traveling at 100 kilometers per hour, and then you stand in the carriage and throw a ball forward, assuming that you are throwing the ball at a speed of 10 meters per second. If you were standing in the carriage looking at the ball, its speed would be the speed of the train plus the speed of your throw, which together would be 10 meters per second plus 100 kilometers per hour. Almost 110 kilometers per hour, right? Whereas someone standing next to the platform looking at it, the speed of your ball would simply be the speed of your pitch, because they can't see the relative speed of you and the carriage. Which begs the question, if you were in a spaceship, you could fire a beam of light in a similar way. So, is the speed of light dependent on where you are and your state of motion or not? Einstein's answer is that the speed of light is always the same, 299,792,458 meters per second, whether you're standing in a compartment or on the Earth. And that even the speed of the spaceship plus the speed of light doesn't push the speed of light beyond that limit whether you're in a spaceship or not. Amazing, isn't it? This is one of the most profound concepts of the theory of relativity, which has updated and transformed many classic physical theories. The wall of the speed of light is in fact closely related to time and space. Through his theories, Einstein pointed out that time and space are not absolute, they are relative and depend on the observer's state of motion. This is the famous time dilation effect. For example, suppose there are two twins, one of whom is traveling in a spaceship at nearly the speed of light, while the other remains on Earth. According to the theory of relativity, the twin on the spaceship will experience a much slower passage of time than the twin on Earth, and by the time the twin on the spaceship returns to Earth, he or she may have experienced only a few years, whereas the twin on Earth may have already experienced a few decades. This is called time dilation. So, in short, the speed of light is not just a speed limit, it actually determines the structure of time and space. Without the speed of light, the laws of physics of the universe would be completely different. The speed of light becomes the ceiling of the universe. You may ask, if the speed of light is so mysterious and insurmountable, why is there such a strict limit? The reason behind this is energy. Simply put, the more mass an object has, the more energy it requires. If you want to accelerate an object close to the speed of light, according to the theory of relativity, as the object goes faster and faster, its mass increases, and more energy is needed to accelerate it further. Near the speed of light, its mass becomes so great that the amount of energy required is almost infinite. In other words, for any object to go faster than the speed of light, it would theoretically require an infinite amount of energy, which is unattainable in reality. To illustrate this with an example, imagine you are pushing a heavy object on Earth. As you push, the object gets faster and faster, but you would need more and more force. If you want it to move at nearly the speed of light, there is virtually no limit to the force required. This process involves not only the mass of the object, but also the conversion and consumption of energy, which is bound by the physical laws of the universe. If we could actually break the speed of light, it could mean that we would have broken the current laws of physics, and even the limits of the law of cause and effect. The law of causality simply means cause and effect. For example, if you break a cup, the cup breaks. Causality is an unavoidable phenomenon in our daily lives. However, going faster than the speed of light could confuse cause and effect, and even create some unpredictable physical phenomena, which may be unacceptable for the stability of the universe. Of course, the scientific community has not completely given up on the possibility of FDL. You can always find some theories about FDL, such as wormholes or negative energy speculations. A wormhole is a hypothetical structure in theoretical physics that resembles a tunnel connecting two different parts of the universe. Through a wormhole, it is theoretically possible to instantaneously travel across great distances in space, seemingly pushing the limits of the speed of light. The problem, however, is that wormholes are only a theoretical idea, and to date there is no actual evidence to support their existence. Even so, scientists continue to explore ways to explore this possibility without violating the known laws of physics. There are many unknown physical concepts involved in these theories, such as negative energy and curved spacetime, which may not yet be fully understood even by our best physicists. Even though we can't go beyond the speed of light right now, the speed of light is still an important benchmark for our exploration of the universe. Whether we measure the distance of the universe in light years or use the speed of light as the standard unit of time, the speed of light certainly provides us with a tool for understanding and connecting with the universe. It is at the heart of the rules of the universe, providing an absolute framework for the relationship between time and space. Scientists use it to calculate the time of interstellar travel, to study black holes, quantum mechanics, dark matter, and other cutting-edge topics, and even sometimes, when discussing other more complex physical theories, we return to the fundamental concept of the speed of light as the starting point for all discussions. Therefore, the speed of light is something that looks like a number, but it holds the deepest secrets of the universe and is a key to our understanding of the universe. 2. Uncertainty principle. The uncertainty principle is actually one of the centers of quantum physics, and it has revolutionized our understanding of the universe. Scientists have discovered that on very small scales, such as the atomic and subatomic levels, we cannot know the exact state of something at the same time. This unknowable state, which we call uncertainty, has been shown to be not just a limitation of our observational techniques, but the very nature of the universe. Let's start with an interesting story. In the early 20th century, when people began to study the microscopic world in depth, scientists felt that matter, like atoms and electrons, should be like tiny particles with a definite position and momentum. But the truth is far from what they thought. But the truth is not as simple as they thought. Werner Heisenberg was the inventor of the uncertainty principle. Heisenberg didn't just come up with this theory, he made his breakthrough discovery by observing a series of quantum experiments. Imagine, in the 1920s, scientists did not have much in-depth understanding of electrons, photons, and other microscopic particles, and it was customary to think that particles were like little balls and that if you knew where they were, you could predict their future position. This is the worldview of classical physics, and everyone basically thinks that knowing enough information will give us a clear idea of what will happen in the future. But Heisenberg thought otherwise. He found that it was impossible to know both the position and momentum, aka velocity and direction, of a particle. It's amazing how small, seemingly insignificant differences can have huge implications in the microscopic world. According to his formula, you will find that the relationship between a particle's position and momentum cannot be fully determined at the same time. That is, if you try to determine the position of a particle through more precise measurements, its momentum becomes ambiguous, and vice versa. To understand this equation more graphically, we can use an analogy. Imagine that you shine a flashlight on a fast-moving ball in a dark room. You will easily be able to locate its exact position in an instant, but because the beam of light itself interferes with the ball's motion, you will not be able to know precisely where it will be going in the next second. This interference with measurements and observations is like a law of nature in the quantum world. It is unavoidable, even irresistible. Heisenberg's uncertainty principle is more than just a mathematical formula. It not only shows that an observer cannot get all the information about the position and momentum of a particle at the same time, but it also sent shockwaves through the philosophy. The discovery breaks with our long-standing intuitive understanding of the world. The universe is no longer a completely deterministic, measurable, and predictable system. More specifically, this means that in the microcosm, things are inherently fuzzy. When you try to measure something accurately, its other properties become less certain. This uncertainty is not due to our lack of technological sophistication, but rather to the fundamental laws of how the universe works. In other words, things in the quantum world simply don't follow the same clear trajectory as they do in classical physics. An electron can be in one position or another. It can have the nature of a particle and exhibit the nature of a fluctuation. This is the fuzziness of the quantum world. The impact of the uncertainty principle is not only limited to the world of microscopic particles, but also makes us re-examine the role of the observer. In classical physics, the observer is objective and does not seem to affect the object of observation, but the observer in quantum physics has become very important. Scientists even say, somewhat half-jokingly, that quantum mechanics is the science of observer-determined reality, meaning that once we make a measurement, the state of the universe is fixed. In a way, it seems that the universe cannot escape the way we observe it. With the formulation of Heisenberg's theory, more and more experiments began to test the validity of this principle. A classic experiment is the electron double-slit experiment, which has revealed the mysterious properties of the quantum world on more than one occasion. In the double-slit experiment, scientists let electrons, or photons, pass through two slits, so that if electrons go like particles, they should pass through one slit and form two clear trajectories. But if electrons are like waves, after passing through the two slits, they form an interference pattern overlapping and interfering like water waves. The result of the experiment was that the electron behaved both as a wave and as a particle, and it was not until we made the observation that we decided which slit it had passed through. Without the observation, the electron behaved as if it had passed through both slits at the same time, creating a fluctuating interference phenomenon. This is very shocking. Can we say that the electron seems to know that we are watching it? Yes, its behavior is influenced by the way we observe it. However you define this awareness, it illustrates a very unique phenomenon of quantum mechanics. We can't dissect the complete state of matter from the outside until we see it. Quantum objects somehow maintain a latent state, which is the wave function in the quantum world, a state with countless possibilities until we observe it. Until we observe it and determine its exact form. This phenomenon has led many philosophers and scientists to wonder, what is reality? Is reality an objective existence, or does it depend on how we observe it? If microscopic particles have an infinite number of possibilities when they are not observed, does this mean that reality itself is somehow dependent on our active observation? Some extreme interpretations suggest that the exact state of reality requires consciousness to give it existence, and that without an observer, there might be no reality. Although this view is a bit too radical, it deeply reflects the impact of quantum mechanics on our thinking. At the microscopic level, the universe does not seem to be a clear, objective reality, but a state of ambiguity and uncertainty. This shift in thinking has had a significant impact on science and technology. This shift in thinking has had a profound impact on science, philosophy, and even art. Quantum physics gives us a new perspective on the delicate boundary between what we know and what we don't know. So, what is the difference between classical and quantum? If you look at it from the perspective of classical physics, the uncertainty of the quantum world seems to be a challenge to classical physics. In classical physics, things always have clear paths and states. You know exactly how fast an object is going, where it is, and even what its future trajectory will be. This is the impression that Newtonian physics gives us. The universe is a precision clock and everything has predetermined rules. But in the quantum world, everything changes. We can't get precise values for a particle's position and momentum without disturbing the system. This is not because our measurement techniques are not advanced enough, but because the universe is fundamentally uncertain. This uncertainty is not accidental, but a fundamental characteristic of quantum mechanics. Therefore, what the uncertainty principle tells us is that things in the world are not always obvious, and very often they are to some extent in a potential state, which will not materialize until we observe them. And this potential state is precisely the most real face of the universe at the quantum level. 3. Mass and energy are equivalent. Have you ever thought that the weight of an object is not only related to its material composition, but also to its energy? What's even more amazing is that these two seemingly unrelated things can be transformed into each other. You may have heard of the formula E equals mc squared, which is an iconic expression of the equivalence of mass and energy. Well, today we're going to take a look at this formula together to gain a deeper understanding of the story behind it and see how it has changed our perception of the universe. To understand the deeper meaning of mass and energy equivalence, we have to go back to the early 20th century. At that time, the scientific mindset was still firmly dominated by Newton's classical mechanics. Newton's view of the world was very deterministic. Objects had fixed positions, velocities, masses, and so on, and it was believed that the universe was like a giant machine, and that the behavior of every object could be predicted precisely by equations. However, with the introduction of Einstein's theory of relativity, especially special relativity and later general relativity, physics entered a whole new field. The theory of relativity showed us a whole new world. Time, space, mass, and even causality can change dramatically in objects moving at high speeds. The most shocking of all, however, has to be Einstein's formula for the equivalence of mass and energy, E equals mc squared. In 1905, Einstein told the world through this formula, mass and energy are actually two things that can be converted into each other. This seemingly simple formula actually contains a very profound meaning that not only changed the fundamental framework of physics, but also had a profound impact on the progress of science and technology, and even the future of human civilization. You may wonder how this formula is so awesome. How can it make the relationship between mass and energy so simple and intuitive? First of all, let me explain to you the derivation process behind this formula. At that time, Einstein was studying the invariance of the speed of light and the relativity of objects, and he found that as the speed of an object increases, its mass will also become larger. Simply put, the faster an object moves, the heavier it becomes. But why is this the case? If an object can go faster and faster, it stands to reason that its mass will increase until it reaches the speed of light and becomes infinite, a physical limit. Einstein's mathematical derivation, combined with the law of conservation of energy, led to the startling conclusion that mass and energy are actually equivalent, i.e., mass and energy can be converted into each other. E equals mc squared, where E is energy, m is mass, c is the speed of light, and c superscript 2 is the square of the speed of light. What this formula means is that there's a constant relationship between mass and energy. The mass of an object actually carries energy as well. This formula seems succinct, but it means a lot of things. We usually think of mass as the intrinsic property of an object and energy as the active property of an object. But Einstein showed us that the two are born together. Their relationship is deeper than we thought, and they are even interchangeable. Having said that, you may find it a bit difficult to understand what's behind this. Why is there such a deep connection between mass and energy? Is it possible that the mass of an object we usually see as its energy? For example, if an object is placed on a table and stands still, is its mass the energy it carries? In fact, Einstein proposed this formula, not to say that the object itself can be converted into energy at will, like the energy in a battery is converted into electricity, but rather, if you make the mass of an object change in some way, for example, through a nuclear reaction, then this change can be converted into a huge amount of energy, and vice versa. Energy can be converted into mass. This is what E equals mc squared really means. Let's take the simplest example, nuclear reactions. We know that both nuclear fission, such as the explosion of an atomic bomb, and nuclear fusion, such as the reactions inside the sun, involve the conversion of mass and energy. In a nuclear fission reaction, the mass of an atom changes, and some of that mass is converted into a huge amount of energy, unleashing the explosive power we see. And the sun, through the process of nuclear fusion, constantly converting the mass of hydrogen atoms into energy in order to continue to shine and heat to maintain the sun's vitality. So, back to our real life, mass and energy equivalence, and what is the significance of it? In fact, behind this formula lies a lot of mystery in our daily life and nature. 1. Application of nuclear energy. Einstein's formula can be regarded as the theoretical basis of nuclear energy technology. Without E equals mc squared, it is difficult to understand how nuclear energy can be so efficient. In fact, nuclear energy utilizes the relationship between mass and energy. In nuclear fission, the mass of matter decreases, but the amount of energy released is extremely large. To take an extreme example, you can take a very small amount of uranium or deuterium-tritium material and convert it into a massive amount of energy, which is why nuclear power generation and nuclear weapons are so powerful. 2. The sun's energy source. The sun is a star that has been able to keep burning for billions of years precisely because of the enormous amount of energy released in the fusion reaction at its core, where hydrogen atoms are constantly converted into helium. In the process, the mass of hydrogen becomes lighter, while the energy released is transferred to the Earth by means of light and heat, sustaining life. 3. Disappearance of matter and conservation of energy. The equivalence of mass and energy also brings us to the idea of conservation of energy. If you imagine that an object has completely disappeared, does that mean that it has lost all its energy? No, it doesn't. According to E equals mc squared, the mass of an object can disappear, but not its energy. For example, if the mass of an object is completely converted into energy, it becomes invisible, but its energy is still there, and it may be transmitted as light. 4. Mass growth of fast-moving objects. Einstein's theory also tells us that as an object approaches the speed of light, its mass increases. This is why you can never make an object go faster than the speed of light. This is because, as an object gets closer to the speed of light, its mass grows and it requires more and more energy, eventually reaching a limit where it can't go faster than the speed of light, even if it were given unlimited energy. You may think that this is just a theoretical formula, but in fact, E equals mc squared is not just a formula in books, it affects every aspect of our modern technology. Do you know about particle gas pedals? It is a technological tool that applies the equivalence of mass and energy. Particle gas pedals increase the mass of particles by accelerating them to near the speed of light. These high-speed particles, when they hit their target, release more energy than any object we see on a daily basis. For example, particle collisions in particle gas pedals are able to simulate physical phenomena under extreme conditions, and scientists continue to reveal the most fundamental laws of the universe through these experiments. Also, you can imagine the nuclear energy technology that we use now, which actually transforms mass and energy by controlling nuclear reactions. In some countries, nuclear power plants utilize this technology to convert and utilize energy safely and efficiently. There's a philosophical view that this formula not only reveals facts in physics, but also indirectly affects our view of existence. If mass and energy can be transformed, then perhaps what we have always thought of as solid existence, whether it be a person, an object, a star, or the sun, is simply a way of manifesting some kind of energy in the universe. What we perceive as the material world may in fact be a transient state of some kind of energy in the universe. In other words, the unity of matter and energy challenges our preconceived notions of the world. It reveals to us that the composition of the universe may not be as stable and certain as we think, but a state of constant change and transformation. 4. Symmetry and brokenness. Symmetry and brokenness are two concepts that are crucial in the construction of the universe and the laws of physics. When you hear the word symmetry, you may think of perfect shapes in aesthetics or geometry, squares, circles, or snowflakes that are perfectly symmetrical. But in physics, symmetry and brokenness mean much more than simple shapes or patterns. They reveal the basic principles of how the universe works. Through these concepts, we can understand why some phenomena in nature seem so harmonious and others so messy. First, let's talk about what symmetry is. In physics, especially in high-energy physics and cosmology, symmetry usually means that the laws of physics do not change under certain transformations. Let's take a simple example. Suppose you have a mirror and you put it in a room. Symmetry means that if you stand in front of the mirror, your left hand becomes your right hand, and the view in the mirror is still a mirror image of you and the room. Here, the presence of the mirror does not change any of the laws of physics, but merely gives a symmetrical reflection. Scientists have discovered that many laws of nature have this symmetry. For example, Newton's classical mechanics is an example of a strong symmetry. In classical mechanics, the translation of an object's motion in time and space is symmetrical. This means that if you move an object from one place to another, or move it forward in time, the laws of motion remain the same. But the fascination of physics often lies in its inversions and complexity, and behind the symmetry lies a fascinating phenomenon called brokenness. The concept of brokenness in physics means that symmetry is not completely maintained in some cases. Imagine you have a symmetrical piece of paper on your desk that starts out perfectly symmetrical. No matter how you rotate it, its shape doesn't change. However, if you gently fold it from one of the corners of the piece of paper, then it is no longer perfectly symmetrical. This folding action breaks the original symmetry. For this piece of paper, this folding can be seen as a break. In the universe, breaking is like this folding process, and often certain rules of nature do not maintain perfect symmetry in all cases. In fact, the symmetry of the early universe is often broken due to certain factors, and this process of breaking is a very important phenomenon in physics. A typical example of symmetry breaking occurs in the Standard Model of particle physics. The Standard Model is a theory that describes elementary particles and their interactions, and it has succeeded in explaining most physical phenomena, but there are some esoteric areas that we do not yet fully understand. One of the most critical is the Higgs mechanism. According to the Standard Model, particles can gain mass by interacting with a substance called the Higgs field. More precisely, this process is due to a phenomenon called symmetry breaking. At the beginning of the universe, about 13.7 billion years ago, the universe was in a state of perfect symmetry at very high temperatures and energies, where there was no mass between particles and all particles moved at the speed of light. But as the universe gradually cooled, the symmetry of the Higgs field was broken, and particles began to interact with the Higgs field to gain mass. This breaking process is actually a revolution in the evolution of the universe. The broken symmetry of the Higgs field allowed particles to acquire different masses, and this difference ultimately led to the formation of all kinds of matter, from elementary particles to atoms, molecules, and the complex life forms we see today. This also illustrates a profound truth. Asymmetry and symmetry in the universe do not exist in isolation. They are in some sense interconnected. The diversity of the universe and matter that we see today is precisely because of early symmetry breaking that led to different particles with different properties and qualities. In addition to particle physics, there is much about symmetry and breaking in thermodynamics. For example, the formation of ice is a classic example of symmetry breaking. Ice is a specific arrangement of water molecules that follows the laws of crystals to form a symmetrical hexagonal structure. During the cooling process, the random movement of the water molecules is restricted and gradually enters an ordered state, breaking its original random symmetry. This process is called spontaneous symmetry breaking. Another common phenomenon is the transition of a material system from an ordered state, e.g., a liquid, to a disordered state, e.g., a gas, near a critical point. This transition process is accompanied by symmetry breaking and restoration. When the temperature of a substance reaches a critical point, the interactions between molecules change, the symmetry that existed suddenly disappears, and the nature of the substance undergoes a fundamental change. If we put this problem on the scale of the universe, the concept of breaking becomes more complex and interesting. After the Big Bang, as temperature and density decreased, matter began to evolve from its initial symmetrical state to a more complex, asymmetrical structure. This process did not only affect the microstructure of matter, but also changed the macroscopic configuration of the universe. For example, during the expansion and cooling of the universe shortly after the Big Bang, the interactions between dark matter, ordinary matter, and radiation gradually separated to form the structure of the universe we see now. And from a cosmological perspective, many current models and theories of the universe involve symmetry breaking. For example, the gravitational and electromagnetic forces in the universe may have been unified in the high-energy state, but as the universe cooled, the original symmetry was broken, leading to the separation of each of these fundamental forces to form the four fundamental forces we see today: gravitational, electromagnetic, weak, and strong nuclear. This breaking process was actually part of the birth of the universe and a very crucial step in its evolution. Without symmetry breaking, the matter and structure of the universe might have looked completely different, and even the existence of life would have become unthinkable. In philosophy and aesthetics, symmetry and brokenness also have profound significance. Many people believe that symmetry represents perfection and harmony, while brokenness represents chaos and imperfection, and imperfections. But in fact, it is these gaps that make up the diversity and complexity of our world. For example, in art and architecture, we often see many asymmetrical designs, which give people a unique sense of beauty. Even in nature, the forms of many creatures are not completely symmetrical, but deviate from the symmetry in some way, presenting more complex forms, and this kind of brokenness often gives people a stronger sense of vitality and dynamism. In short, symmetry and brokenness are the two faces of the operation of the universe. Symmetry keeps some basic laws of the universe unchanged and provides us with a basis for exploration, while brokenness is the fundamental force that drives the diversity and evolution of the universe. The two appear to be opposites, but they are in fact complementary and indispensable. This relationship between symmetry and brokenness not only occupies a central place in physics, but also provides profound insights into our understanding of nature, life, and the universe. The marvelous thing about the universe, perhaps, is that it has always found a delicate balance between symmetry and brokenness, and it is this balance that has contributed to the richness and complexity of the world we see today. 5. The principle of the centerless universe. The principle that the universe has no center is an interesting and profound concept, centered on the idea that the universe itself has no fixed center or boundary. This may sound confusing and even a bit counterintuitive, since almost everything in our daily lives has a center of some kind. For example, the Earth is the center of our lives, the Sun is the center of the Earth, and even each of us often feels that we are centered in some sense. Center. But when we stand on the scale of the universe, this way of thinking in terms of centers no longer applies. Let's understand this from an astronomical perspective. Traditionally, human beings have always thought that the universe has a fixed center. For example, the ancient Greeks thought that the Earth was the center of the universe. This idea lasted for thousands of years until Copernicus proposed the heliocentric theory, that is, the sun is the center of our solar system, and the Earth and other planets revolve around it. This idea overthrew the geocentric theory of the time and marked a giant leap in the history of science. However, the universe is much bigger than we can imagine. When we say universe, we don't just mean our solar system, the Milky Way, or even all the galaxies. In fact, modern astronomy has taught us that the universe is a huge system of tens of billions of galaxies, and that the system itself has no fixed center. You may be thinking, well, if the universe has no center, where is the boundary of the universe? This question is actually more complicated than one might think. The universe we see now is actually just a part of the universe. Scientists have hypothesized that the universe is expanding based on the phenomenon of redshift, which is the change in the wavelength of light. This means that the universe has been expanding since the Big Bang, and that this expansion is uniform. No matter where you stand in the universe, you will see other galaxies moving away from you. There is no center, and what every observer sees is an expansion. The Big Bang Theory is a key to understanding the principle that the universe has no center. According to this theory, the universe began to expand about 13.8 billion years ago from an extremely dense and hot state. This initial expansion did not begin at a point, but rather at every location throughout the universe at the same time. In other words, the expansion occurred everywhere, not just at a specific center. To better understand this process, scientists often use the analogy of a balloon expanding. Suppose the universe is a balloon, and each point on the balloon, representing galaxies, is expanding away from the other points. But the balloon itself does not have a fixed center. The center we perceive is only relative to where we are looking. To further help understand the concept of a centerless universe, let's move on to a more relevant example. Suppose you are standing on a plane with no boundaries that extends indefinitely. Anywhere you stand in it, you feel like you are in a part of the plane. However, no matter where you go, you will never be able to find a center because the plane has no center. If you fly to a distant city and open the windows of the plane, the whole city will seem to revolve around you from the plane's point of view. You don't feel that the city has a center because it expands uniformly, and any place can be considered a center. Similarly, the expansion of the universe is like this infinite plane, where every point is expanding and no place is the absolute center of the universe. Further, the principle of the centerless universe is also related to Einstein's cosmological constant. Einstein introduced the cosmological constant in his theory of relativity, initially to describe a static model of the universe. But with later discoveries, scientists realized that the universe was not standing still, but was expanding. This process of expansion does not have a specific center, but occurs uniformly everywhere. The uniformity of this expansion and its lack of a center also means that any point in the universe can theoretically serve as a starting point for an observer. For example, when we stand on Earth and look at the stars, the galaxies may appear to revolve around the Earth, but from a cosmological point of view, the Earth is just a tiny point in the expanding universe, with no special characteristics at all. 6. 4 fundamental forces interacting with each other. Have you ever wondered how everything in the universe interacts with each other? From the daily interactions between you and me, to the movement of planets and galaxies, to electrons orbiting around the nucleus of an atom, there is a mysterious force behind it all. These 4 forces are the building blocks of the universe. We often refer to these forces as fundamental forces because they are the underlying driving force of all physical phenomena. Imagine if we can understand the mysteries of these 4 forces, we may be able to reach the deepest part of the universe and unveil the deepest veil of nature. The 4 fundamental forces are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Let's talk about these forces one by one, how they interact with each other, and how they shape the universe as we see it. 1. Gravity, the gentlest pull of the universe. When you think of gravity, the first thing that probably comes to mind is the moment the apple falls from the tree, or why the moon doesn't fall in the sky. Gravity is the most common force in our daily lives, perhaps the most intuitive, but it also has the most elusive characteristics. The basic principle of gravity is that any object with mass will have an attractive force on the objects around it, and this force is proportional to the mass of the objects and inversely proportional to the square of the distance between them. This is the famous Newton's law of gravity. Doesn't it sound so simple? But this is the law of attraction of the universe that Newton came up with in the late 17th century, and it is still the basis of our understanding of the motion of celestial bodies today. You might be thinking, shouldn't this force be at work here on Earth and between you and me? But in reality, gravity is everywhere. It doesn't just make apples fall, it also makes the Earth orbit the Sun, the Moon revolve around the Earth, and even keeps the stars and planets in the entire Milky Way galaxy moving in relative paths. Although Newton's theory of gravity was very successful, it had one limitation, which was that it could not fully explain the nature of gravity. And it was only after Einstein proposed the theory of general relativity that the true nature of gravity was revealed. Einstein proposed that gravity is not a visible force, but a curvature of spacetime. Objects are free to fall in this curved spacetime along a certain trajectory, just as a ball rolls on an elastic fabric, following a curved path. One of the most famous proofs of this theory is the gravitational lensing effect, whereby a distant object, such as a black hole, bends spacetime and affects the trajectory of the light we observe, bending the light like a lens, and even allowing us to see objects that are obscured. This is one of the most mind-blowing results of general relativity. 2. Electromagnetic force, the ubiquitous force field around us. The second fundamental force is electromagnetism, which governs almost every phenomenon around us. From the flow of electrons to the existence of magnetic fields, from the propagation of light to the radiation of electromagnetic waves, the influence of the electromagnetic force is omnipresent. The electromagnetic force consists of two components, electricity and magnetism. Electricity acts on charged particles, while magnetism acts on moving charged particles. You can imagine a negatively charged electron being attracted around a positively charged nucleus in an electric field, and as it moves along in orbit, the resulting motion creates a magnetic field. The combination of electricity and magnetism produces a myriad of phenomena that we can perceive. A classic example is electromagnetic induction. When a conductor moves through a magnetic field, the change in the field creates an electric current inside the conductor. This discovery was made by the famous physicist Michael Faraday in 1831 and paved the way for later electric power technology and the theory of electromagnetic waves. As you know, the principles behind modern devices like electric motors, generators, and transformers are almost inseparable from the electromagnetic force. Another fascinating example is light. Light is actually a form of electromagnetic wave, a fluctuation of alternating electric and magnetic fields. It travels at a very fast speed. The speed of light is about 300,000 kilometers per second. This speed is not only the limiting speed of electromagnetic waves, it has also become a fundamental constant of modern physics. The wonderful thing about electromagnetism is that it is one of the most common forces we come into contact with in our daily lives, yet it has an exceptionally wide range of applications. It is behind almost every modern technology, from cell phones to TVs, from radios to X-rays. 3. The weak nuclear force, mysterious interactions between particles. Next, we'll talk about the weak nuclear force, a name that sounds a little strange. It is the shortest range and most mysterious of the four fundamental forces we recognize. The main action of the weak nuclear force is within atoms, especially in nuclear reactions and radioactive decay. The weak nuclear force does not directly affect the motion of celestial bodies on large scales like gravity, nor is it as prevalent in everyday life as the electromagnetic force. It has a very short range of action and is significant only on the scale of atomic nuclei. It is a key factor in the decay of some particles. For example, in a process called beta decay, the weak nuclear force causes a neutron to transform into a proton and emit an electron and an antineutrino. This process is not only a fundamental reaction in atomic nuclear physics, but also an important mechanism in the universe. Although the weak nuclear force is so weak, that it is hard to notice, it played a huge role in the formation of the universe. Without the weak force, stars would not be able to produce energy through nuclear reactions, and the elements of the universe would not exist in the way they do now. So the weak nuclear force, even though we hardly feel it in our daily lives, does play an important part in the deep structure of the universe. 4. The strong nuclear force, the glue of the universe. Finally, we come to the strong nuclear force, the most powerful force in the universe. It is the force that binds the protons and neutrons in the nucleus of an atom, allowing the nucleus to remain stable and not to be repelled by the same charges in the electromagnetic force. Why is the strong nuclear force so important? Without it, protons would not be able to form stable nuclei due to the repulsive effect of the electromagnetic force. The strong nuclear force is very powerful, but its range of action is very short, confined to the scale of the atomic nucleus, about 1/10,000,000th the size of protons and neutrons. One of the famous experiments that demonstrated the role of the strong nuclear force in particle collisions was conducted by the European Centre for Nuclear Research, CERN. In these high-energy collisions, the strong nuclear force glues particles together to form new particles, a process known as particle creation. The more mysterious part is that the strong nuclear force does not manifest itself directly through collisions between particles. Scientists have discovered that the strong nuclear force is transmitted between protons and neutrons by a particle called a gluon. A gluon is actually a massless particle that maintains a strong attraction between protons and neutrons through constant exchange. These four forces appear to be independent and have different scopes of action, but they are inextricably linked in the evolution of the universe. Einstein's unified field theory is an attempt to fuse these forces into a unified framework, specifically the connection between the electromagnetic and weak nuclear forces. As physics continues to evolve, scientists are beginning to try to unify these forces in some way through experiments and mathematical models. Although scientists have yet to find the perfect unified theory, every experiment and every discovery is a step towards that goal. 7. Scale invariance. Did you know that there seems to be a mysterious force in the universe that makes structures at different scales follow similar patterns? This scale invariance is particularly evident from the microscopic to the macroscopic scale. You can imagine that galaxies and clusters of galaxies are distributed in a way that is somewhat similar to what we see in nature here on Earth. They all exhibit a certain fractal character. When you think of fractals, you might think of mathematical equations, complex shapes, or some kind of artwork. In fact, fractals are a very special kind of geometric form, which can be found everywhere in nature and in human artistic creations. For example, the shape of a snowflake, the outline of a cloud, the distribution of tree branches, and even the network of blood vessels are all expressions of fractals. This scale invariance means that no matter how much you zoom in or out of a structure, the overall shape and distribution pattern remains the same, like a self-similar structure. When it comes to the universe, scale invariance is especially evident in the large-scale structure of the universe. If you zoom in and out of the universe a few times, the distribution pattern of galaxies actually has a lot of similarities to the distribution of clusters of galaxies that we observe. For example, in terms of large-scale structure, the distribution of galaxy clusters tends to show a huge web-like structure, like the spider's web of the universe. These webs connect galaxies and clusters of galaxies, and when we reduce the scale to the distribution of galaxies and even stars, you will be surprised to find that, although the scale varies greatly, but the overall structure still has a similarity. Just as you look at the distribution pattern of tree branches, no matter how you look at it, the distribution of branches and leaves have a self-similar pattern. If you have seen images of the large-scale structure of the universe, you may have noticed that galaxies and clusters of galaxies are not randomly distributed in the images, but show a network-like structure. This structure is similar on all scales, which is a manifestation of scale invariance. Scientists also call this phenomenon the cosmic web, a vast network of structures from stars and galaxies to clusters of galaxies. One of the most profound mathematical innovations of the 20th century was fractal geometry, which centers on the idea that the details of certain geometric forms are similar at different scales. The idea first originated with the French mathematician Benoît Mandelbrot. By studying irregular forms in nature, such as mountains, clouds, and the paths of rivers, he discovered that they are not simple geometric shapes, but rather structures with self-similarity, i.e., whether you zoom in or out of it. Its structure and form don't change much. In his 1975 paper, Fractal Geometry, The Geometric Forms of Nature, Mandelbrot suggested that the geometric properties of fractals could be used to describe many phenomena in nature. Since then, fractal theory has not only caused a sensation in the mathematical world, but has also had a wide impact in the fields of physics, astronomy, geography, and meteorology. Fractal geometry gives us a whole new way of thinking. It breaks the limitations of traditional Euclidean geometry and is able to deal with more complex, irregular, and unbounded forms. The difference is that the scale of the universe is simply too big, spanning from galaxies to clusters of galaxies on scales too large to be imagined. Let's look at how galaxy clusters demonstrate this scale invariance. In astronomy, galaxy clusters are giant structures made up of thousands of galaxies. They're like the cities of the universe, harboring large amounts of matter and dark matter. It has been found that the distribution of galaxy clusters follows a pattern of scale invariance. On large scales, we see that the clusters form a kind of network structure, and this structure reflects a similar pattern on small scales. There is an interesting story behind this phenomenon. In 2005, scientists observed the Milky Way neighborhood clusters and found that the distribution patterns of these clusters were very similar at different scales. In order to verify this, astronomers adopted the theoretical framework of scale invariance, and through calculations and simulations, they found that the distribution of galaxy clusters did show similar structural patterns at different scales, proving that scale invariance is universal in the structure of the universe. Interestingly, scale invariance is not only reflected in the macroscopic scale of the universe, but it also has a very important manifestation in the microscopic quantum world. Traces of scalar invariance can also be seen in some phenomena in quantum physics, especially in the study of high-energy physics. For example, in the particle collision experiment, scientists found that the interaction of particles is not with the increase in collision energy and become more complex, but there's a trend similar to the simplification. This phenomenon is the embodiment of scale invariance. Physicists have proposed a theory called scale-invariant quantum field theory, which suggests that the fundamental constituent particles and force fields of the universe may follow a scale-invariant law, meaning that their properties remain the same at different scales. This is a rather esoteric theory, involving the intersection of high-energy physics, cosmology, and quantum mechanics. In general, however, it implies that there may be some underlying unity and similarity in the universe between the microcosm and the macrocosm. The existence of scalar invariance also provokes some philosophical reflection. For example, are humans just limited to a particular scale to observe the universe, and are there higher or lower scales that we cannot directly perceive? If the structure of the universe is so similar at different scales, does it not also explain how we human beings look for the unified laws of the universe from the microscopic world of particles? These questions have given rise to extensive discussions among scientists and philosophers and have contributed to the trend toward the intersection of physics, cosmology, and philosophy. 8. Vacuum energy. You may be thinking, vacuum energy? Isn't that just empty? Yes. Vacuum sounds like nothing, empty. But in fact, the vacuum of the universe is not simple, which hides a lot of mystery. In a vacuum, there is actually energy present, and it is even sometimes closely linked to major cosmic phenomena such as cosmic expansion and dark energy. Do you remember that air bubble you used to play with when you were a kid? When you pinched it, it broke, and it seemed to be air inside, but air is not as easy to touch as solid or liquid. The concept of a vacuum is kind of like this bubble. You say it's empty, but it doesn't seem to be completely empty. We often hear the term nothing, but in the eyes of physics, this emptiness is very specific and is not the complete absence of anything that we think it is. Vacuum does not mean dead silence, it is actually full of quantum ups and downs. Quantum mechanics tells us that particles and antiparticles don't stay still forever, They pop out of the void from time to time and then quickly disappear. It's like an actor suddenly appearing on an unseen stage and immediately retiring without leaving a trace. We can call these particles, which appear and disappear briefly, virtual particles. These virtual particles do not destroy the overall emptiness of the vacuum, but their presence makes the vacuum no longer dead, but full of activity. This process is called quantum flux. Scientists have indirectly proved the existence of this quantum fluctuation through an experiment called vacuum polarization. As a simple example, you can imagine that in an empty room, some light spots suddenly appear and disappear instantly. Although the existence of these spots of light does not bring any substantial changes to the room, but their flashes show that the room is not completely empty, it is actually latent potential or energy. So what is the connection between vacuum energy and the dark energy we hear about? Dark energy is a hypothesis put forward by scientists when studying the rate of expansion of the universe. It is an invisible, omnipresent energy that drives the universe to expand faster. Originally, we thought that the expansion of the universe should slow down due to gravity, but in fact, astronomers have discovered through observations of distant supernova outbursts that the expansion of the universe is accelerating, and dark energy is thought to be the culprit for this phenomenon. In quantum mechanics, the vacuum is not completely devoid of energy. Vacuum energy, or the energy of the vacuum, is the energy generated in the vacuum due to quantum fluctuations. In other words, even if we pump a space as clean as possible, with almost no matter, there is still vacuum energy in it. Some scientists have hypothesized that if vacuum energy does exist, and it is associated with dark energy, then vacuum energy could be one of the causes of the accelerated expansion of the universe. If the entire universe is filled with this potential energy, it would act as an invisible push to keep the universe expanding. Just like astronauts floating in space, although they can't see any force acting on them, they are still being pulled further and further away by the expansion of the universe. Of course, the connection is not entirely clear, and scientists are still exploring the mystery. There's still a lot that's unknown about the exact nature of vacuum energy and whether it's directly related to dark energy. So how exactly was vacuum energy discovered? The process is closely related to the revolution in quantum mechanics in the early 20th century, when Heisenberg, one of the founders of quantum mechanics, proposed the uncertainty principle in the 1920s, which revealed that the position and momentum of particles in the microscopic world could not be precisely determined at the same time. This idea opened the door to a new understanding and led people to rethink the nature of the vacuum. Then, in the 1930s, the famous physicist Paul Dirac proposed the concept of virtual particles. These virtual particles are not really stable particles. They are always in a state of constantly changing energy and extremely transient. Through these studies, scientists have come to realize that the vacuum is not absolutely empty, but an energy field full of possibilities. However, it was in the 1990s that vacuum energy really attracted widespread attention. At that time, astronomers discovered that the expansion of the universe was accelerating through the observation of distant supernovae. Scientists began to link this phenomenon to the existence of dark energy and further hypothesized that vacuum energy could be one of the sources of this mysterious energy. In other words, the tiny amount of energy produced by the kind of quantum rise and fall in the vacuum may have had a profound effect on the expansion of the entire universe on a macroscopic scale. If the vacuum continues to exist, and it does not change in future evolution, the expansion of the universe will continue to accelerate, eventually leading to an end called the Big Freeze. This means that as the universe continues to expand, galaxies will become farther and farther apart, and eventually all the stars and galaxies will move away from us because of the expansion, and the universe will gradually become darker and cooler until there are no more new stars or life. Of course, there are other possibilities. Some theories suggest that the vacuum energy is not static and unchanging, and that it could change over time, even leading to some kind of turnaround in the accelerating process of cosmic expansion. But all this still needs more observations and theoretical studies to reveal. Well, that's it for this installment. Likes and comments welcome. Thanks for watching.